Bismillahirrahmanirrahim. Assalamu alaikum. Students, I hope you all are doing well. Welcome to online lecture 1 of industrial pharmacy. Today we are going to start our first unit, which is heat transfer. This unit is divided into 2 lectures. In this lecture we will be discussing the part 1. Let's first start with the definition of heat. So what is heat? Heat is the form of energy that is transferred between systems or objects with different temperatures, flowing from the high temperature system to the low temperature system. It is also referred to as heat energy or thermal energy. Heat is typically measured in calories or joules. हीट क्या है? हीट एक फॉर्म ऑफ एनर्जी है जो ट्रांसफ़र होती है बिटवीन सिस्टम्स या ऑब्जेक्ट्स जिनके डिफरेंट टेम्परेचर्स होते हैं. मोस्टली हीट फ्लो करती है हाई टेम्परेचर रीजन से लो टेम्परेचर रीजन तक, और इसे हम हीट एनर्जी या थर्मल एनर्जी भी कहते हैं. हीट टिपिकली मेजर होती है इन टर्म्स ऑफ BTU या फिर कैलोरीज या जूल्स की फॉर्म में. Moving further to our actual topic, that is heat transfer. Let's see what is heat transfer. According to the thermodynamic systems, heat transfer is defined as the movement of heat across the border of the system due to a difference in temperature between the system and its surroundings. Interestingly, the difference in temperature is said to be a potential that causes the transfer of heat from one point to another point. Besides, heat is also known as flux. So heat transfer क्या है? थर्मोडायनेमिक सिस्टम के अकॉर्डिंग हीट ट्रांसफ़र को हम डिफ़ाइन कर सकते हैं मूवमेंट ऑफ हीट की फॉर्म के अंदर, जो कि एक बॉर्डर सिस्टम के अक्रॉस मूव करती है ड्यू टू अ डिफरेंस इन टेम्परेचर between these two systems and its surroundings. For example, this is a border system and there is a difference between two temperatures. One is a higher temperature and the other one is a lower temperature. Interestingly, जो difference in temperature है इसे हम potential कहते हैं, जो actually heat को transfer करवाता है from one point to another point. Heat को हम इस सूरत में flux भी कह सकते हैं. So how is heat transferred? Heat can travel from one place to another place in several ways. The different modes of heat transfer includes conduction, convection and radiation. Heat transfer कैसे होती है? Heat different ways के अंदर travel कर सकती है from one place to another place, और 3 different modes हैं heat transfer के: conduction, convection or radiation. Meanwhile, if the temperature difference exists between the two systems, heat will find a way to transfer from the higher to the lower system. Like here in this case, heat is transferring from the higher to the lower system. We will be discussing each of these processes in detail. So let's start with the conduction. What is conduction? The energy transmission occurs by transmission of momentum of individual molecules. This is the definition of conduction. The energy transmission occurs by transmission of momentum of individual molecules. An area of higher kinetic energy transfers thermal energy towards the lower kinetic energy area. Like here in this case, this is the area of higher kinetic energy and this is the area of lower kinetic energy. It transfers the thermal energy towards the lower kinetic energy area. High speed particles clash with each other, moving at a slow speed. As a result, slow speed particles increase their kinetic energy. This is a typical form of heat transfer and takes place through physical contact. Conduction is also known as thermal conduction or heat conduction. So conduction क्या है? एनर्जी ट्रांसमिशन की अकरेंस बाय ट्रांसमिशन ऑफ मोमेंटम ऑफ इंडिविजुअल मॉलिक्यूल्स इज कंडक्शन। एक ऐसा एरिया जिसके अंदर हायर काइनेटिक एनर्जी एग्जिस्ट करती है, वो ट्रांसफ़र करता है, हायर काइनेटिक एनर्जी ट्रांसफ़र करती है थर्मल एनर्जी को टूवर्ड्स दी लोअर काइनेटिक एनर्जी, ऐसे एरिया के अंदर जहाँ पर लोअर काइनेटिक एनर्जी है। हाई स्पीड पार्टिकल्स क्लैश होते हैं, जो कि मूव करते हैं एक लो स्पीड पे, जिसकी वजह से लो स्पीड पार्टिकल्स इंक्रीज करते हैं अपनी काइनेटिक एनर्जी। ये टिपिकल फॉर्म ऑफ हीट ट्रांसफ़र है और मोस्टली फिज़िकल कांटेक्ट के थ्रू होती है। लाइक हियर इन दिस केस बर्नर इज इन फिज़िकल कांटेक्ट विद दिस पॉट। Conduction is also known as thermal conduction or heat conduction. When heat is flowing under steady state condition, the quantity of heat transfer is given by the following equation, where capital Q is equals to Ka multiplied by T1 minus T2 theta over L, or it can be expressed as a small q Ka T1 minus T2 upon L, where the capital Q is the quantity of heat, A is the area, T1 minus T2 is the temperature difference, theta is time, L is the thickness, and K is the constant of the material, which is also known as coefficient of thermal conductivity, and Q, small q, which is used here in this equation, is quantity of heat transfer per unit time. The constant K, which is the characteristic of any material, is known as coefficient of thermal conductivity, and it can be defined as it can be defined by putting all other factors in equation equal to 1, like area, temperature difference, and thickness. Thus, the coefficient of thermal conductivity is the heat passing in unit time from one phase of a cube unit side to the opposite phase, the temperature difference being kept at 1 unit. जब हीट फ्लो करती है अंडर स्टेडी स्टेट कंडीशंस, तो क्वांटिटी ऑफ हीट ट्रांसफ़र को हम इस इक्वेशन के थ्रू एक्सप्रेस कर सकते हैं, विच इज़ इक्वेशन नंबर 1. दिस इक्वेशन नंबर 1 कैन बी रिटन एज इक्वेशन नंबर 2 एज वेल, जिसके अंदर हम एक्सप्रेशन ऑफ टाइम को पर यूनिट टाइम के अंदर एक्सप्रेस कर रहे हैं. कैपिटल क्यू क्वांटिटी ऑफ हीट है जो ट्रांसफ़र हो रही है पर यूनिट टाइम, और ट्रांसफ़र हो रही है इन अ सर्टेन अमाउंट ऑफ टाइम. ए एरिया है, T1 माइनस T2 इज़ द टेम्परेचर डिफरेंस, थीटा इज़ द अमाउंट ऑफ time which is used for the transference of heat from the higher temperature area to the lower temperature area. L is the thickness, K is constant for the material, which is also known as coefficient of thermal conductivity, and small q is expressed in this equation, equation number 2, where theta is deleted. This is the quantity of heat transfer per unit time. अगर हम K को डिफ़ाइन करें तो K एक कैरेक्टरिस्टिक है किसी भी मटेरियल का, जिसे हम कोएफिशिएंट ऑफ थर्मल कंडक्टिविटी भी कहते हैं, और इसे डिफ़ाइन करने के लिए हमें बाकी तमाम फैक्टर्स को इक्वल टू 1 रखना पड़ता है. कोएफिशिएंट ऑफ थर्मल कंडक्टिविटी को जब हम डिफ़ाइन करते हैं तो हम ये कहते हैं कि हीट पासिंग इन द यूनिट टाइम फ्रॉम वन फेज ऑफ अ क्यूब यूनिट साइड टू द ऑपोजिट फेज, and the temperature difference being kept at 1 unit is known as coefficient of thermal conductivity. Thermal conductivities vary considerably, ranging from metals that have high values through non-metallic solids and liquids to gases that have the lowest values. Typical thermal conductivities for a range of materials are given in this table. For example, a metal which is copper has a thermal conductivity of 379 watt per meter Kelvin. Aluminium, which is also a metal, has a thermal conductivity of 242 watt per meter Kelvin. Steel has a thermal conductivity value of 43 watt per meter Kelvin. Stainless steel has a thermal conductivity value of 17 watt per meter Kelvin. Borosilicate glass has a lower thermal conductivity value, that is of 1 watt per meter Kelvin, and water has a lower thermal conductivity value than borosilicate glass as well, that is 0.6 watt per meter Kelvin. So is the boiler scale's thermal conductivity value, which is again lower than water, and it sometimes is greater than water. Therefore it has a range which is from 0.09 watt per meter Kelvin to 2.3 watt per meter Kelvin. Diatomite is another substance which can be used as a material in transference of heat, and it has a thermal conductivity value of 0.07. Glass wool has a thermal conductivity value of 0.06, which is very lower, and air has a thermal conductivity value which has the least value, which is 0.03 watt per meter Kelvin. सो ये डिफरेंट थर्मल कंडक्टिविटी वैल्यूज़ हैं जो डिफरेंट मटेरियल्स के लिए डिफरेंट हैं मगर कांस्टेंट हैं. इन्हीं थर्मल कंडक्टिविटी वैल्यूज़ को लेते हुए हम एग्ज़ाम्पल को सॉल्व कर सकते हैं. फॉर एग्ज़ाम्पल हमने इक्वेशन 1 और इक्वेशन 2 देखी थी जिसके अंदर अमाउंट ऑफ हीट ट्रांसफ़र हम कैलकुलेट कर सकते थे. So that equation can enable the heat flow to be calculated for a particular set of circumstances. So let's see an example. Here the question says calculate the amount of heat that will flow through a sheet of a steel 10 millimeter in thickness, 0.6 meter wide and 1 meter long in 30 minutes with a temperature of 70 degrees Celsius on one side and 30 degrees Celsius on the other. So question ये कहता है कि अमाउंट ऑफ हीट कैलकुलेट कीजिए जिसमें हीट फ्लो हो रही है स्टील की शीट से, जिस स्टील की शीट की थिकनेस 10 मिलीमीटर है और ये 0.6 मीटर वाइड है, 1 मीटर लॉन्ग है, और ये हीट ट्रांसफ़र हो रही है इन 30 मिनट्स. टेम्परेचर डिफरेंस स्टील के आउटसाइड और स्टील के इनसाइड ये है. आउटसाइड टेम्परेचर इज़ 70 डिग्री सेल्सियस and to which the heat would be transferred has a temperature of 30 degrees Celsius. So let's see what is the data for this example. Thickness is expressed as L and it is 10 millimeter. We will convert this into meter, which will be 0.01 meter. Area here is presented in the form of length into width. So we'll multiply the length into width and we'll have 0.6 meter square of area. Time given here in is theta, which is 30 minutes. We'll again convert it into seconds. 30 minutes are equal to 1800 seconds. Temperature 1 or T1 is 70 degrees Celsius and temperature 2 T2 is 30 degrees Celsius. Coefficient of thermal conductivity for steel is 43 watt per meter Kelvin. So let's put these values into the equation, which is Q Ka T1 minus T2 theta over L. Here it is expressed in this. A coefficient of thermal conductivity is 43 multiplied by 0.6 meter square, which is the surface area or area of steel, and then the temperature difference, the high temperature minus lower temperature 70 minus 30 multiplied by the time, which is 1800 seconds, and divided by the thickness of the steel sheet, which is 0.01 meter. So this will give you a value of 185,760,000 joules, which can be written as 185.57 megajoules. So the amount of heat transfer from the sheet of steel in 10 minutes with a temperature of 70 degrees Celsius outside and 30 degrees Celsius on inside and an area of 0.6 meter square will give you the amount of 185.57 megajoules that is transferred from one side to another side. However, a difficulty arises in the compound layer of several materials of different thermal conductivities since the overall conductivity cannot be obtained by simply adding together the individual conductivities. The problem can be overcome by rearranging the equation 2 like this, in this form, where equation 2 can be written as Q is equals to T1 minus T2 over L over K. This is the specific case of heat transfer by conduction of the general expression representing any rate process, where rate can be expressed as driving force divided by resistance. This, the temperature difference, is the driving force of the heat transfer, and it will be realized that the resistance to conduction will increase for greater thickness and will decrease as the coefficient of thermal conductivity increases and as the area becomes larger. डिफ़िकल्टी उस वक्त अराइज़ होती है जब हम कंपाउंड लेयर्स की बात करते हैं, जो कि ऐसी कंपाउंड लेयर्स जो सेवरल मटेरियल से बनी हुई होती हैं और उन कंपाउंड लेयर्स में से हीट को ट्रांसफ़र होना है. अब हर मटेरियल की डिफरेंट थर्मल कंडक्टिविटी वैल्यूज़ हैं, इसी वजह से ओवरऑल कंडक्टिविटी को हम ऑब्टेन नहीं कर सकते बाय सिंपली एडिंग टुगेदर द इंडिविजुअल कंडक्टिविटीज़. Like if you are using steel and copper at the same time, you cannot add the conductivities of steel and copper and find the overall conductivity of the compound layer. इस प्रॉब्लम को ओवरकम करने के लिए हम इक्वेशन 2 को रीअरेंज करते हैं इस फॉर्म के अंदर, जिसमें स्मॉल q कैन बी एक्सप्रेस्ड एज T1 माइनस T2. स्मॉल q मतलब amount of heat transfer per unit time can be expressed as T1 minus T2 divided by L over K. ये स्पेसिफिक केस उस वक्त हो सकता है जब कंडक्शन एक्सप्रेस हो रही हो या जनरल एक्सप्रेशन कंडक्शन की हो रही हो एज अ रेट प्रोसेस, किसी भी रेट प्रोसेस के थ्रू. और अगर हम रेट को डिफ़ाइन करते हैं तो रेट इज़ डिफाइंड एज द ड्राइविंग फोर्स डिवाइडेड बाय रेजिस्टेंस. इस केस के अंदर टेम्परेचर डिफरेंस ड्राइविंग फोर्स होती है फॉर हीट ट्रांसफ़र, और ये रियलाइज़ किया जाता है कि रेजिस्टेंस इज़ एक्चुअली द रेजिस्टेंस टू कंडक्शन विल इंक्रीज़ फॉर ग्रेटर थिकनेस. रेजिस्टेंस कंडक्शन के अगेंस्ट इंक्रीज़ होगी जब थिकनेस इंक्रीज़ होगी, और ये डिक्रीज़ होगी एज द कोएफिशिएंट ऑफ थर्मल कंडक्टिविटी इंक्रीजेस एंड एज द एरिया बिकम्स लार्जर. Recalling the theory of electricity, the conductivities cannot be added together to obtain the total conductivity of the circuit, but the overall resistance in the number of resistances in a series is obtained by taking their sum. अगर हम theory of electricity को recall करें तो कंडक्टिविटीज़ को हम ऐड नहीं कर सकते टोटल कंडक्टिविटी को ऑब्टेन करने के लिए किसी भी सर्किट की, जबकि ओवरऑल रेजिस्टेंस को हम ऐड कर सकते हैं नंबर ऑफ़ रेजिस्टेंसेस में किसी भी सीरीज़ में बाय टेकिंग देयर सम, और हम ओवरऑल रेजिस्टेंस फाइंड आउट कर सकते हैं. Furthermore, the resistance and conductivity bear a simple relationship to each other, being inversely proportional. Applying the electrical analogy to the heat transfer means that the overall resistance to heat transfer of a number n of layers can be obtained by adding the reciprocals of their thermal conductivities, that is expressed as resistance is equal to 1 over K1 plus 1 over K2, so on and so forth till 1 over Kn. इलेक्ट्रिकल एनालॉजी को अगर हम अप्लाई करें हीट ट्रांसफ़र सिस्टम में तो हम ये कह सकते हैं कि ओवरऑल रेजिस्टेंस टू हीट ट्रांसफ़र हम डिटरमाइन कर सकते हैं किसी भी n नंबर ऑफ़ लेयर्स का बाय एडिंग द रेसिप्रोकल्स ऑफ देयर थर्मल कंडक्टिविटीज़. दिस अज्यूम्स दैट द लेयर्स आर ईच ऑफ यूनिट थिकनेस. थिकनेस यूनिट है, L over K को अगर हम एक्सप्रेस कर रहे हैं तो यहाँ पर यूनिट थिकनेस है, ठीक है, which is very unlikely, so that the allowance must be made for this, and this resistance can be expressed like this. Resistance is equals to L1 over K1 plus L over L2 over K2 and so on and so forth, and it would lead till Ln over Kn. Generally, the area of conduction will be same for each layer, but if it is not, an additional area term may be included. To calculate the heat transfer, we need to know the overall thermal conductivity, which can be obtained by reversing the process, that is by taking the reciprocal of the process of overall resistance. Usually this is known as the overall coefficient of heat transfer and is represented by U, and it can be expressed as U is equals to 1 over L1 over K1 plus L2 over K2 till Ln over Kn. हीट ट्रांसफ़र को कैलकुलेट करने के लिए हमें ओवरऑल थर्मल कंडक्टिविटी को फाइंड आउट करना पड़ता है, जिसे हम ऑब्टेन कर सकते हैं बाय रिवर्सिंग द प्रोसेस, दिस होल रेजिस्टेंस प्रोसेस, that means by taking the reciprocal of the overall resistance, and it is usually termed as the overall coefficient of heat transfer, which is expressed as 1 over L1 K1, which is the reciprocal of this overall resistance. To calculate the heat transfer, U is used instead of K over L in equation 2, and it can be expressed as Q is equals to UA T1 minus T2. Heating of fluids. When a liquid is to be heated, the process is commonly carried out in steam heated vessels similar to the jacketed pan. At first sight, it might appear that there would be a simple temperature gradient through the wall between the steam and the liquid. Whenever the fluid contacts the surface, there will be a boundary layer, and being stationary, the heat must be conducted through this layer to the bulk of the liquid. Also, it is likely that some scale will have been deposited on the surface of the metal wall, and heat must be conducted through this. When steam gives up its latent heat, water will condense on the surface of the vessel, and it will form a condensate film. Again, the heat must be conducted through this water film. Furthermore, air exists as in the jacket before heating begins, and some may remain in the steam. The air will not remain as clearly defined film, but there will be a greater number of air molecules adjacent to the surface. For the sake of simplicity, therefore, it will be assumed that the air is present as a stagnant layer or stagnant film through which heat must be conducted. The situation is rather more complicated than a first impression here in this figure. With this figure, figure 1 suggests the diagrammatic form of figure 2 being nearer to the truth. The temperature gradients suggest that the various layers are likely to exert a considerable effect on heat transfer, the extent of which can be best seen from a numerical example. The values assigned to the thickness of the various layers are hypothetical but are of the correct order. So, जब liquid को हम हीट करते हैं तो प्रोसेस कॉमनली कैरी आउट होता है स्टीम हीटेड वेसल्स के अंदर या स्टीम जैकेटेड वेसल्स के अंदर. फर्स्ट साइड के अंदर ये देखा जा सकता है एक सिंपल टेम्परेचर ग्रेडियंट है थ्रू दी वॉल्स बिटवीन द स्टीम एंड लिक्विड. लेकिन जब भी लिक्विड फ्लूइड कांटेक्ट में आता है सरफेस लेयर की, तो एक बाउंड्री लेयर और एक स्टेशनरी लेयर हमेशा प्रेजेंट होती है. अगर आप इस फिगर 1 को देखें तो इसमें टेम्परेचर ग्रेडियंट थ्रू हीटिंग सरफेस एंड फ्लूइड को आइडियलाइज किया गया है. Like there are different layers which are present from this heating surface till the liquid. First layer is of steam, जो कि obviously steam jacketed vessel के अंदर है. Second layer is of air film. Okay. थर्ड लेयर इज़ ऑफ कंडेंसेट फिल्म, वाटर जो कि टेम्परेचर डिफरेंस होने की वजह से कंडेंसेट हो रहा है. फोर्थ लेयर इज़ अ स्केल. Fifth layer is the metallic wall, which can, in this case, if we are considering a stainless steel jacket, then it is a stainless steel. Sixth layer is a liquid film, which is the boundary layer for the liquid, and the seventh layer is the liquid itself. So for the heat to transfer from one side to another side of the container, that means from the source till the liquid, there are different boundary layers present. In this idealized state, there are 7 layers. In this actual form, steam is followed by air film, and it is followed by a condensate film, and then it is followed by a scale, metal wall, liquid film, and liquid. The difference in the thickness varies here in this idealized condition, where here in this actual condition, whereas in this idealized condition an exact thickness is present. In normal circumstances or in actual circumstances, the difference in thickness exists. That means the thickness varies for each layer or each boundary layer, for which the heat is transferred from one side of the container to the other side of the container. So we can actually see this by an example. The question says a steam jacketed pan with a steel wall 5 mm in thickness is being used to heat water. Calculate the overall coefficient of heat transfer using the following data, which says there are almost 6 films: an air film, a condensate film, a scale, a steel wall, a scale, and then a water film. The thickness of each layer is given here as L1, L2, L3, L4, L5, and L6, and the coefficient of thermal conductivities of each films are given here, being the highest as the steel wall, which is 43. By putting this data into the equation of overall coefficient of heat transfer, we can see that the result obtained is 94.94 watt per meter square Kelvin. So the overall coefficient of heat transfer in steel wall having different boundary layers or different layers is 94.94 watt per meter square Kelvin. Clearly a value of about 95 watt per meter square Kelvin for a wall 5 mm in thickness is very low when it is considered that steel has a thermal conductivity that can conduct 4300 watt per meter square Kelvin for a wall 10 mm in thickness. Other metals are better conductors of heat, for example copper, which has a thermal conductivity of 379 watt per meter square Kelvin, and substitution of a copper wall should increase the value of the overall coefficient of heat transfer. So repeating the calculation with the copper instead of steel, here the whole question is same. We have just replaced the copper wall with the steel. So is the coefficient of thermal conductivity, which was 43 for steel, and here is 379 for copper wall. So we put this data into the equation of overall coefficient of heat transfer, and the result obtained is 95.88 watt per meter square Kelvin. Comparison of the two values shows that although the thermal conductivity of the metal wall is almost 9 times greater, the overall coefficient of heat transfer has changed from 94.94 to 95.88 watt per meter square Kelvin, which is a negligible increase. Obviously, factors other than the metal wall are involved, and the answer lies in the other layers as well. So that is the end of this lecture. In next lecture we will discuss design of heating equipment, heat transfer by convection and radiation heat transfer. Thank you for patiently listening to this lecture. For your queries, use HULMS or we can discuss in the physical class. Allah Hafiz.